Fine. Hello, 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 hello. Hey, Power Path. You're the one with the WCCA, right? The worst case analysis. Hey, tell me about you, Power Path. Where are you? Are you in the U.S. or somewhere else? Oh, you're from India. Okay. Now, why are you interested in worst case analysis? It's kind of complex, a little difficult. It's very time consuming, actually. I guess, what is the interest of, is it for work, I guess, that you're trying to do worst case analysis for work? Or is it for student? Or are you in college, I guess? I'm just curious. Okay. Anyway, worst case analysis, there's certain things that you. Oh, okay. I see. Working on these currently, and I feel it's interesting to get to know about electronics better. Okay. Yeah. Well, when you do a worst case analysis, you have to build a database, uh, basically, of all your parts. Uh, for example, if you have a resistor, you have to find out what the temperature coefficient is of it. And then uh, you have to, so you get a spreadsheet. Uh, and so one of the parameters is temperature. So on the when you have a temperature and you have a temp code on the resistor, then you have to calculate. Oh, and then you have to find out on your circuit what is the operating temperatures that's going to be operating. So let's say I'll just give an example. Like in space, uh, I've seen operating from -30 to about 60 degrees C. So then you have to uh, do a database of your resistors of how much resistance will it change over that temperature from -30 C all the way to 60 C. So you'll have a delta resistance due to temperature. Then the second parameter is aging. So let's say the mission is, let's say space mission is 7 years. So then you have to calculate, okay, how long or how much will this resistance change if uh, if it's in space or whatever for 7 years. Now to do that, you have to use what is called the Arrhenius equation. Okay, look it up. I think it's ARE. Yes, NIO. NIOUS, Arrhenius equation. It's an equation that I think was developed for chemistry. It's a like chemical reaction, and you type in certain numbers in there. So, and that data is usually, like for example, in resistors, they do lifetime testing. Like for example, they'll test the resistors, let's say for 2,000 hours, and then after 2,000 hours, oh, and they accelerate it. In other words, they do the testing at a higher temperature to simulate, aging. So, so they'll test, let's say, 2,000 hours, and then once they age them or test them under heat or whatever for 2,000 hours, they have to meet a certain percent tolerance. So, so if they test and they meet that specification, then the data, like 2,000 hours, and let's say they can only change, let's say 1%. That data, the 2,000 hours and the 1% change goes into the Arrhenius equation, and then that calculates or it projects logarithmic me like 20 years into the 7 years into the future how much it will change. So so you get a number. Okay, so you go with temperature, aging, and I think that's what you do on those two, on resistors. Is temperature, yeah, temperature and aging. Those are the two main ones. Those are the ones that you do. So so then you're gonna get, so that's the first thing, and you have to do the same thing for, let's say, your diodes. You have to and your diodes, your MOSFETs, everything, all of that, you have to, for every parameters, you have to calculate certain parameters and so forth. And now the only difference is in semiconductors, you have to do the temperature, and then you have to do the aging, but then you also, in space, you have to account for radiation. So that's another biggie. So on resistors, I don't think we I don't think we do analysis for radiation. I think they're inherently uh, not susceptible to changes due to radiation. Or at least I don't remember doing that. But I know that in semiconductors we do uh, radiation analysis. Uh, some numbers, we use some worst case analysis guides. I might have some book here. Let's see if I have. Yeah. Okay. I'm sorry, guys. I'm talking about Power Path. He's been asking about worst case analysis. So here's this. Okay, and it's from let's see, Design and Evaluation Incorporated. So this is a introduction. So there's two. This is volume one and volume two. So okay, so remember I was talking about a database. Okay, so you got to do like a little worksheet. Here's an example. Okay. Oh, okay. So this is for resistors. Here's an example. So this is for a RWR81 resistor, and they have the initial tolerance, high temperature, low temperature, radiation none, and they actually have a number for moisture, life, and that's mil spec standard 199, and so forth. So anyway, let's see if you can see this. Does it show up? I have it upside down? No, it's backwards. It looks different. It comes out backwards in reverse. But anyway, so you total up your biases and your randoms, and then you end up with this number. Well, actually, here, worst case, you get a minimum of 1.9%, a maximum of plus 1%. And so you get your worst case, and then you also have what is called drift. So you got this takes a lot of time. I mean, extremely amount of time. Yeah, I'm sorry. Yeah, it says Carlos. It's mirrored. Yeah, it's mirrored. So anyway, so you gotta do that for your parts, for every single part, and it's just really time consuming. So once you have that, and you know how much your parts, then what I do, I use spice, and the spice that I'm using is top spice, and in top spice, uh, there's a, directive. Uh, Basically, oh, okay. So I use top spice. Okay. So then that's database is number one. That's the first thing. Then the second thing that you have to do the worst case analysis is you have to do a sensitivity of the circuit. So what does that mean? So like let's say you have a power supply and you have a remember in most power supplies you have two dropping resistors. You know, you have a resistor that goes to V out, and then you have another resistor go down to ground, and then the middle one usually goes to the error amp. So the sensitivity means if you increase the resistor, let's say in the you increase it up, will the voltage go up or does it go down? So if it goes up, that means it's got a positive sensitivity, and if it goes down, then it's a negative sensitivity. So you have to do uh, sensitivity of all the parts that are in the control circuit. So that takes quite a bit of time to do. So there is a in Spice. There's a under. I think it's in the operating. Uh, there's a sensitivity analysis, and you type in, like say V out, and then what it does uh, on the sensitivity analysis, then on the printout, then each part it'll say what is the sensitivity. In other words, is it a positive or a negative? So once you do that, then you have to identify everything, and then you have to make that all the increments of each resistor or each part are added. In other words, you want all the errors to add in the worst case. So I'm going to do a video on that because it's kind of hard to explain it with words. It's much easier uh, if I show how to do it on video. So, but it's going to take about maybe two or three videos to do that. So just kind of be patient with me, Power Path. I'll, that's something that I'll do. I guess there's seven other people here, or is that something that a video on worst case analysis, is that something that would benefit other people as well? Okay. So what other subjects are? I know that someone last week. Oh, by the way, today I had a hard time trying to get in. Okay, Carlos has a good question. Would you recommend build a prototype? type power supply on a proto board, or is it better to proto them directly? Okay, that's a good question, Carlos. Okay, I'm ready for you. Okay, I'm going to show you. Okay, make sure that it's off. Okay, hang on. I got to disconnect. I have to unsolder something so I can show you. Okay. Don't use, those little breadboards where you stick the, I mean, only if it's a simple circuit, then yes. But if you're gonna try to prototype a power supply, then no. Let me see. Okay, I'm back. Okay, Carlos. Okay, when it comes to power supplies, these are not very useful. Okay, you can't. It doesn't handle very much power. And then uh, the higher frequency you go, then the capacitance between the two slots or the plates, they interfere. So you can't do RF with these. At least they're not that useful. Okay. So so the biggest thing is you need like a power plane, a real good power plane. So what I've done is, like you mentioned, prototype on a PCB board. This is what I've been doing. This is just a regular board, really. Okay, so these boards I buy them cheap at Tayada. I think they're somewhere in Thailand. I think there's 6x6 copper. Okay, and so I use that. Okay, so the other thing that you can use. Okay, just bear with me, guys. Okay, there's two ways that you can attach the parts. I hope you can see this. Does it come out well? Can y'all see? Okay, so this is a 150 watt synchronous converter. It's a prototype. Okay, so hopefully you can see. Okay, so there's I think there's a ham radio operator that sells these. I think they're called me pads, me pads. Okay, and these you can break. They're little squares. You can break them. Like for example, well, I don't want to break these. Hang on, let me see if I can break a different one. Okay, so you can break them into pieces. See. So then what you do is use super glue. Right, you put the super glue on the back, and then you glue them down. Okay, so then you can solder components. So this is isolated from this. Okay, and you can put two, and then you can put resistors, and this is a combination of that. Okay, so I use meat pads. Now the other thing that he also sells is he sells little these. as well. So that's how I prototype. Now the other thing that I've been using instead of the meat pads, the only thing that I don't like about the meat pads is they let's say if I have a transistor hooked up and I'm burning a lot of power. Hang on. Okay. Oh man, I feel like I'm in school. Show and tell, where you bring your projects and show and tell. Okay, so the other option is, oh, and I think this method of prototyping, I think it has a name called Manhattan. Okay, so you have the meat pads. Let me see. I have maybe one or two meat pads, but most of these connections are actually done with diamond tips. These are diamond tips. So you get yourself a little. You need a drill press. You cannot use a hand drill. If you try to use a hand drill, you're gonna scratch it up. These are diamond tip, uh, and what it does, it makes you can make holes, not holes, but it does a little round. Let me see if I. Okay, this here's a good example. Okay, so these you buy yourself a little driver, a drill press. Okay, because the drill press, yeah, has a little handle and it pulls it down, and you hold it real tight. And what it does is, as it spins, it does this. Does it make? Can y'all see that? See, it cuts and it leaves little islands. Does that come out? I think it does. See, those are the little islands. So then you can solder to there. You don't need to. You don't need a meat pad. See, so that's what most of these are. You might be able to see this one right here. Right there. That's a big cutout. See the cutouts? Right there, you can see two round ones. There's another two round ones. So that's how you can attach stuff. The nice thing about this is that it's a good ground plane. Okay. And if you put the wires close, then you should get something uh, much less noise. So get yourself a drill press, and you can buy these in on Amazon, and you can get them from different thickness. And get yourself some are not that good. So if you find a pair that works good, keep using them. And then the other thing that you need is sometimes you may have to drill holes, so you need some real good drill bits. So those those are the ways that I would recommend uh, to use. Gurap Singh, hello. Yes. Okay. So that's the way I prototype uh, uh, power supplies, or at least some. After a while, if you have a design that already works, then you don't have to prototype. You can reuse your the same circuits. Now, if you have a real simple circuit, and it's not very power hungry, then yeah, you can use these. Okay, so there's nothing wrong with this, but it's just Just remember that they're kind of limited. I do have one just in case I need to put a little circuit together. Okay. Okay. Any other questions? Okay. Can you post the worst case video later based on your available time? But just make pictures and designing closed loop box. Okay. Uh, okay. This is for PowerPoint. Uh, to to close the loop on buck is the same as closing the loop on a two switch forward. Okay, and it's very similar to closing the loop on a discontinuous flyback. So so basically, my mentor taught me to, which was Jack Alexander. Uh, you do pole canceling. Okay, basically. So the main uh, transfer function. The transfer function of the plant is a low pass filter. So it goes at a certain gain, and then you have your pole, and then the ESR kicks it up, you know, gain. So if you have a pole on your power supply, then your error amp you want to put at the same frequency. You want to put a zero. So the pole and the zero they cancel each other. And then right here on the plant where you have a zero, then you want to put a pole on the error app. So you want to cancel. So you want to cancel two positions, and that's basically the trick that Jack Alexander helped me. Now go ahead, and I do have a couple of videos on loop compensation. They're on flybacks. If you understand the concept doing a discontinuous flyback, then doing a boost or a buck or a two switch forward, it should be basically principally the same principle. So you're just going to cancel the poles with zeros and so forth. So it's kind of intuitive. But take a look at those. If you still have problems, email me, and maybe we can Skype. Aquino, no, Akanimo. Hi, how you doing? Okay. Hey, Carlos, where you writing from? I'm just curious. Carlos Eduardo Ornales. Oh, Carlos, eres de México. Oh, ¿qué parte de México eres? Sorry, guys, I'm talking Spanish. Aquino, oh, Nigeria. Wow. Carlos, oh, de Jalisco. I think I have family there. Yeah. Wow. Yo nací en Nuevo Laredo, Tamaulipas, México. Me inmigré a la edad de 3, so no tengo mucho recuerdo de mi juventud. Tenía 2 o 3 años cuando me inmigraron. Guadalajara. Wow. Yeah. En Guadalajara tengo ah, tengo familia. Se llama Bolaños también. Wow. Aquino, Nigeria. Hi, how you doing? Wow. Okay, that's good. Power Pass. Oh, you Power Path is from India. Wow, that's good. Arian. Hi, Arian. How you doing? Where you from? Well, Sergio has a good question. How do you generate a pole zero cancellation over several output loads? Okay, that's a good question. Okay, usually when you, at least in power systems, when we get a requirement, one of the first things that we ask is what is the your load variations. In other words, what is the minimum and what is the maximum? Okay, so as long as we know what is our load requirement, then we can compensate. I mean, we don't have to put the we cancel them exactly. We can, put them in the middle. I think what Jack did was if there was two positions, I believe he used the geometric mean. And I think the geometric mean is, let's say if the pulse moves, let's say from 100 hertz to 1 kilohertz, I believe you multiply 100 hertz times 1 kilohertz, you multiply it and you get the square root. And that gives you, I think, the geometric mean. So then he put the pole right there where the geometric mean. So I think that's the way he did it. The other thing that if you're going to get a requirement, you want to make sure not only do you want the load requirement, a lot of things that a lot of people forget is when your power supply gets connected to, let's say, another board, okay, you as a power designer, you need to know how much capacitance does the other board have, because once it's connected, the capacitance that is downstream, in other words, the capacitance that your board is powering, you have to compensate for that. So when we get that, we ask, the other engineers, well, how much capacitance? And then what we do is we hang extra capacitance at the output, and then we compensate. So we make sure that our compensation will work under the loads, minimum load, maximum load, and also uh, under their load, capacitive load. Okay, so you want to make sure that. Okay, so Vivek, India. Hi, how you doing? I have a lot of friends. Raj, I don't know if you're there. I've been working with Raj. He's in India. I have another friend, Anand from India. You Indians are awesome engineers. You guys, you're cranking a bunch of engineers. It's surprising how many engineers. And not only engineers, medical doctors, scientists. Is like y'all. Your universities are world class institutes. They're really really uh, smart there. So anyway, so I hope that answered your question, Sergio. Yeah, the Indians are very smart. They're smart. Yeah, I asked some of my Indian friends that I've what is it in their why how is it that they have a, at least from my perspective, how is it that they produce so many engineers? And the feedback that I got was that it's in their culture they value teachers, I believe was number one, and then yeah, teachers, engineers, and then doctors, and maybe lawyers not so much. I thought so. I don't know if any of my Indian friends online can verify that or not. If yeah, Carlos says mathematical minds. Yeah, well, they just well, okay. There's no secret. Okay, Uh, to be good at anything, uh, you just have to study hard. It just takes a long, long, long time. There's a book. It's called The Outliers. Okay, and this book called The Outliers, the author, what he does is he studies people that are very good in the professions. And one of the first things he does is he studies like soccer players, and he studies like why are they so good. And he turned out from studying them that the ones that are like the Messi or Rivaldi, these superstars, they've been playing soccer since they were like barely walking. They put a lot of time. They were obsessed with it. So and then he found out that he did the same study like for pianists. You had like the high level pianists and then the average pianists and so forth. And then he asked, how many hours did you practice and stuff like that? And sure enough, the ones that were elite pianists were the ones that were practicing like 6 hours a day. And then the average, maybe 4 hours a day. So it just depends. Uh, Engineering is the same way. And I guess in every field, the more you put time into it, the better you get. Uh, anyway, so he comes up with a rule. Says to be good in anything, you have to put about 10,000 hours. 10,000 hours to be good. So anybody that is good in engineering, I'm pretty sure they put more than 10,000 hours in learning their craft. Okay. Narendra, mine. I'm sorry if I butcher your names. Hello, how you doing? I'm glad, Narendra. An email, very interesting information on the remote capacitor composition. Yeah, yeah. You. Oh, Vivek says, yeah. Teachers and professors are well respected. Yeah. Hey, Vivek, how about lawyers? Are they held in high esteem and doctors? I would assume, let's say, a medical doctor would be held in high esteem as well. Am I right or wrong? Or what's the ranking? In other words, what would be like? Let's say, Indian mother and father. What do they tell the kids to be? Like here in the U.S., they say doctor, lawyer, and like maybe engineers, maybe sometimes. But I always hear doctor and then lawyer, and I don't hear too many engineers, but I would say engineers. So in India, so if you can let me know. Oh, he says tell them to be either engineers or a doctor. Okay, yeah. So there's a big emphasis in your culture to uh to excel. Uh, so yeah, yeah, Indians are very smart, but everybody can be as smart as Indians. So okay, and let's see who else is on. Narende, what advice would you give for a new analog engineer like me? I'm very much into analog design and working since last many years. But I still want to be best at engineer. Can you advise? Okay, I think I mentioned this. I got on uh, last week uh, online trying to figure out how to do this. I had trouble today. I'm still learning how to get online. But anyway, uh, if you're an analog designer, and this goes for power engineers, guys, Power Path, Vivek, Nemo, learn how to do spice. That's what I mentioned last week. If you learn how to do spice and how to model, man, that's to me that's the number one skill. Okay, because once you do uh, uh, s- once you know how to use spice, you can uh, simulate the circuit instead of prototyping it. You can simulate much faster in spice, and you can learn uh, a lot from doing spice. So you can actually gain a lot of experience from doing spice. So if let's say if you're a new college grad, do a project in spice. Actually, that's how I got my job at Southwest Research. And yeah, spice is like very. Yes, I like to simulate my circuits, and then we actually do an engineering board. Uh, Now I do this here because this is my home project. At work, we actually do a PCB board. Okay, and we'll do engineering one. If it's a new project, let's say it's a development, something that like let's say a high voltage pulsar. That's something that we never done before at where I work. So, and that took about 7 years to develop it. So I've had to go through several revisions. So once you do the revisions, I always like to see and measure the actual board and then compare with my simulations. So, and if they don't agree, then I fix my model to make sure that they agree. And then I can do what if simulations. So that's a big thing. So learn how to spice, learn how to simulate stuff. Uh, the other another thing to learn in spice is how to do parametric sweeps. Parametric sweep. Let's say if you have a resistor, let's say you have a non-inverting op amp. So you have the feedback resistor and then the input resistor, and let's say you want to increase the resistance of your feedback. Well, if you increase it, you increase the gain. And let's say you could do a spice and you can do an AC model, right? And then you can do a parametric and then sweep, and you can see the gain, AC gain, move up. So that's neat to see that and learn how to do that. Okay, Vivek, take care. So anyway, that's one of the things that I would suggest as an analog designer or power, learn how to do some spice. That would be, and then there's a bunch of applications. A lot of the data sheets. That's another good place. Data sheets. A lot of time will have sample circuits, and they want to get you to use their chips. So one way is looking at the application notes and the data sheets, and they'll show, and they'll have like a circuit explanation of how circuits work. Some of the older application ones, the ones that were done maybe 20, 30 years ago, oh, the ones from Jim Williams, those were really good. I mean, that's why he became famous because his uh, application notes were so good. So, yeah, any if you can get, I think they were either Linear Technology. Is that who he worked for? Jim Williams. So, yeah, he's try to read some of his application notes. They're really good. So, oh, okay, many years in the industry, but I still miss the perfection. Well, are you doing like not Narendra? So, are you doing power electronics or are you doing VLSI design? I guess is my question. Okay. Hi, Adrian. He's asking if there's any recommendation for thermal management on high voltage power supplies. Ah, okay. Yeah. Okay. Nadendra, he's she or uh, okay, is a analog integrated circuit design. Okay, hang on. Let me see. I'm looking for a book. Hang on. See if I can find my book. Darn it. Okay, I was going to show you a book. Actually, my okay. Here's something interesting for you, Nadendra. Yeah, integrated circuits. Okay. Okay. Oh, so see, Narendra has got special skills. Okay, because he, or I'm not sure. Narendra, is that a female name or a male name? I'm not sure. Anyway, uh, okay. Well, now they're asking. Okay, you're a man. No, I'm a man. Okay, I'm sorry. I apologize. Sorry, sorry, sorry. Okay, dummy me. Okay, my training was in VLSI design. So I went to the University of Idaho to learn how to become a integrated circuit designer. I wanted to become, and the reason was at the time I was working at Sony Semiconductors in San Antonio, Texas, and I was I worked in the fab. I was a wet etch engineer. So and being a wet etch engineer is kind of like a dangerous job because I work with uh, dangerous chemicals. And Narendra would, uh, if he works in a fab or is close to a fab, he'll know that wet etch, you use sulfuric acids, BOE, buffered oxide etch, uh, all sorts of aluminum etch stuff. Uh, I forgot already the chemicals, but you could drop like a napkin or a cloth and it would disappear, eat it up. So it was a dangerous work environment, and I didn't want to do that. So I started taking classes, uh, distance learning to pick up some design classes in VLSI. So yes, my degree is actually in VLSI. I want to become chip designer for Sony. Unfortunately, in 2004, Sony decided to shut down the fab in San Antonio, Texas. So, and I had worked there 8 years in Sony Semiconductor. So here's another piece of advice for everybody. Uh, if you're in engineering or the technical, you have to be flexible. And when I say flexible, you have to learn different skills. You have to reinvent yourself. Okay. So here's a quick background of the things that I was before. My first job was a TV repairman. I started actually very young at the age of 12. And the reason that I started very early is because I had three uncles that were TV repairmen. So in the summers, I used to work with them. So I learned electronics at a very, very early age. So when I graduated, my first job was at RCA Service Company. I was driving a van, making service calls, fixing TVs. And to me, that was a perfect job for me. I thought I would be a TV repairman for the rest of my life. But then during that time, it was 1994, RCA started laying off people. And I knew sooner or later I would get laid off. And I was already, I think, 26, 26. So I ended up going back to school, and I went to engineering school at a late age at 26. So a lot of y'all went to school at 18. I went to school at 26. I was already married. I could not go full time. I had to work part time and go to school part time. So what took what takes 4 years to graduate, it took me almost 10 years. So I was 35 years old when I graduated. So and I went to school to become an engineer. I had already been a technician 22 years. So that's my point. You have to change because sometimes your job will go away, or they'll shut down and you don't have a job and you have to feed your family, and you have to pick up a skill. So my first job as an engineer was at Sony Semiconductor. And the skills that I had as a TV repairman did not help me at Sony. At Sony, I had to pick up pneumatics, hydraulics, chemicals. I had to pick up a lot of skills. So you have to be real flexible. So I became an edge engineer. And then when that Sony shut down, okay, RCA shut down, and I worked 13 years there. And then I go to Sony, and then I work 8 years, and they shut down, and I have to reinvent myself again. So I went to Motorola as a product engineer or QA. You have to learn new skills. You have to be flexible. You have to do things that that's in demand. So I only did 1 year of Motorola because I hated the job. It was I didn't like it. It was more production. There's no creativity. I like to design. I always like to design or fix. So I got lucky in 2004. I got into Southwest Research, and I never designed a power supply. I knew how power supply designed and that worked, but I never designed one. So I had to. Luckily, by that time, I had already started my master's and I was doing a lot of simulations. So the learning spice really helped me because when I went and interviewed at Southwest Research, uh, I actually simulated a buck converter and I used the K factors to compensate the power supply. So then since then I've been working diligently to pick up the skills. And some of these skills I try to pass to you guys with uh, through some of my videos. So anyway, so that's the advice. You have to pick up new skills. Okay, you never know. Your job might go somewhere else, or the company will fall down, and you have to learn new things. Don't get stagnated. Uh, oh, here's another piece of news. That's great variety expensive. Okay, here's another thing. Okay, this is good advice. So, spice, learn new skills, be flexible. Okay. The other thing that I would advise for your careers is make yourself indispensable. And what do I mean by that? Okay, at Sony, at okay, I'm gonna go back to uh, my experience at Sony. At Sony, I I became an wet edge engineer, and uh, no one wanted to work on the pumps. Not even the technician wanted to work on because the pumps would break down, and and the chemicals were dangerous. So, in order for me to find and to be hired, and actually, when I got hired as an intern, and I wanted to make myself valuable, so I started working on these pumps. So basically, I did the shitty jobs. So sometimes uh, you find job security when you do jobs that no one else wants to do, and if you do it good, then you become the expert or whatever. So if there's a particular something that no one wants to do, but you don't mind doing it and you can do it good, then do that. So you become then to the company, you become like indispensable because you have certain skills. So in other words, find a niche, something that that the company values, and that you like to do. And if you like to do it and they value it, then they'll keep you around and they'll compensate you. So that's the other thing. So if you find something that no one wants, but that they want to do, but they need. Okay. So like Power Path, I don't know if you're in there. WCCA, that's something that a lot of people don't like to do. But if you like to do it and it's something in demand, I would pick up worst case analysis. Okay, any other questions? Let's see. Yeah, I think that's why Power Path is so interested in worst case analysis. Yeah, because that's something that I don't like to do the worst case analysis. It's just because it's very time consuming. But there is a company in California, uh, Analytic Engineering, I think. That's by Charles Himowitz. They're probably the best uh, WCCA company in the world for that. They're really good. Charles is good. As a matter of fact, Charles Himowitz, uh, he was a co-founder of Intusoft. Intusoft is a spy simulator. So he was one of the co-founders. Him and Charles Larry Mears, I think, was the other co-founder. So yeah, so Charles Himowitz, he's really good at in spice. Okay, do we have any other questions here? Please, Ernesto. Have we met, Ernesto? Can you give me some more? We may have met, Ernesto. Okay, Sergio asked a question. I'm sorry, Sergio. So, do you ever design an inductor current sense amplifier using discrete components for switching power supplies operating in megahertz? What kind of challenges did you face? No, you know what? We okay. In space, we okay. I see that you're operating in the megahertz. Okay, in space, we operate at 100 kilohertz to 200 kilohertz. We don't go up in the high megahertz. There's a good reason for that. Uh, if you're going to be operating in the megahertz, you have advantage that you can get a linear technology MOSFET or controller that will operate in those frequencies. Okay, I can't. I can't use off the shelf components. I'm limited on the parts that I can use. I have to use radiation hardened MOSFETs and radiation hardened integrated circuits, and uh, those devices, they're not suited for high frequency that high. So we're always limited to 100 kilohertz to maybe 200 kilohertz. So now, for current sense, we usually use a current transformer. So we use a 1 to 100 turns or a 1 to 50 turns. So that's what we use to do the current sense. The only problem that I have is uh, if you use an amplifier, the only concern would be if it would be fast enough uh, to sense it, or if it offers any phase shift. Because let's say if you have a current mode control, and let's say you have a shorten the output, you want to sense that as fast as possible. But if there's a little bit of delay through the current sense amplifier, will that prevent pulse by pulse current mode from protecting? So that's the only thing that I would be concerned. Okay. Let's see, what time is it? Oh, okay. Yeah, I think I okay. I didn't see Sergio's. Can you comment a little bit more on the kind of technology used in space? Yeah, everything has to be radiation hardened. Uh, the MOSFETs are typically uh, they're in metal cans. They're not. We can't use plastic. Any MOSFETs with plastic we can't use. I think the plastic with radiation it degrades. So that's a no plastic parts. Like for example diodes. If we use diodes, they have to be glass encased. Okay, the MOSFETs have to be encased in metal, so no plastics are allowed, or we don't use that. Uh, uh, Capacitors. We use tantalums capacitors like CWRs, 29s. Those capacitors we can use. Those are solid tantalums. We use stack capacitors or ceramic stack caps. We use those uh, because of the low ESR, and yeah, you just have to be careful uh, that you don't crack them. Uh, yeah, ceramic capacitors. If you flex the board, uh, they can develop little cracks, and depending if it's shift, you can have a short. So you have to be real careful with ceramic capacitors. They're very delicate, especially if let's say as they get bigger, the capacitors. Let's say they become, let's say, a half an inch by half an inch, that big, and you solder them. Then you can't solder them with, I believe, the soldering iron because it creates a temperature gradient, and you're more apt to cracking the capacitors. So you have to use a hot air gun, something like this. Okay. And I believe some of our fabricators, if they installed a capacitor, a ceramic capacitor, onto the board, they have to preheat the board, bring it up to a certain level, and then they apply the heat. So they want to get the temperature across a large ceramic capacitor, they want to keep it as even as possible, because if you heat up one side and this side is still cold, that the thermal gradient can, or difference gradient, will crack. So you got to be sure you do that. What kind of tests are used to check circuits that won't fail under high radiation environments? How do you simulate it under spice? Ah, Adrian, that's a good question, Adrian. How do you know about that, Adrian? It says, Adrian said, for your space applications, did you ever experience VG threshold degradation of your FETs that you have had to compensate for ahead of time? Yeah, that's usually, okay, that's why you can't use regular MOSFETs. They have to be radiation hardened FETs. I think I covered this. Uh, as radiation, the way my understanding is, um, MOSFETs, when they get radiated, if the gate oxide is real thick, if it gets, if you have a real thick oxide and you have a particle ion and it gets stuck in the gate oxide, well, that little particle is a charge. And let's say another charge gets stuck in there. Eventually, the threshold voltage, and let's say you have a threshold of 3 volts. Well, to turn on the MOSFET, you have to exceed 3 volts, the threshold voltage. Then the MOSFET turns on. But then with radiation, that VG threshold, because of the charges, they start going down and lower and lower. And if it goes down to zero, that means any voltage above zero will turn it on. But then when you go back to zero, it's still on. It doesn't turn off. You would have to go to negative voltage to turn it off. So that's the main problem, that if you, let's say if I was to use one of these MOSFETs, just the regular MOSFETs that we all use, the plastic ones, and they're not radiation hardened, then with time they won't be able to turn off. So that's a biggie. So that's why we use radiation hardened MOSFETs. No, we don't test on a cyclotron. What we do is, or okay, let me backtrack. Uh, IR, I think it's Infineon. Uh, I think there's very few companies that do radiation parts, and these, we already know that they've been tested up to a certain level, and they'll test them up to maybe 100 k rads, and I think the highest I've seen is 300 k rads. So it's a certain level of TID, total induced dosage or something like that. So you know that they'll operate up to that level. So you're pretty much assured that they're going to work. So companies, uh, when they introduce a new product, they do testing. And one of the products that we did do is this one. This is a GANFET from GAN systems. So we did do. Uh, we wanted to use these parts, but we had to screen. We couldn't use just regular. They had to be screened and tested to certain testing criteria. And that we did use. We did some testing. The engineer that did the testing is a guy named uh, Roberto Montreal. He's from Spain. He did testing at the Texas A&M. They have a radiation facility there, and some kind of a cobalt isotope or something like that. And so he irradiated them, and then he checked the parameters and see how they change. So from that data, he then tells me you can use this. uh, f- uh, GAN fed up to this voltage. So that's how we get uh, uh, our criteria as far how to test. So basically, the components are tested, okay, ahead of time, and so we get components or MOSFETs that are already proven to work. So, but once we do the product, we don't test them for radiation. We do test them for a thermal cycle. We do that, and we go to vibe testing, and then we also do EMI testing as well. Yeah, Tamu has yeah, yeah, they do have that. Yep. See, we have a guy here that knows Plisken. He knows probably more about the testing. What kind of range do they do the testing? Well, that's a good question. Oh, well, when we do thermal, the spacecraft is, I believe, uh, they already have an idea what the spacecraft is going to be operating at. That information then gets fed to us, the designers, what temperature we're going to be operating at. So, uh, because in space there's no air, right? There's nothing to blow the heat away. So to get the heat out, let's see. So if most of the power supplies they go in a card cage, okay. So the heat is going to be by conduction, right? So you put your components uh, close to the edge. That way, heat flows to the edge, and then from here to the edge to the frame of the box, and then from the frame to the spacecraft. So there's no fans. It's all by conduction. Uh, so that's how we do that, and a lot of that is done by and layout. Our layout guys are really good. They're world class. They've been doing that for over 30 years, so they know how to get the heat out and use a lot of copper as well underneath. I do remember we did have a project where we put like little copper heat sinks. There was an issue that it was a long project. This mission had like many years, and they were afraid that with time, with the cycling, they would develop cracks. So we had to do special mounting uh, for that, and I think they had to mount them backwards with the pads up, and then put wires to the board, kind of like a strain relief on that. Okay, already. It's okay. 5 more minutes. I'm gonna take off at 11. It's 10:55. Okay, automotive. Oh man, Narendra. That's more severe than us. Actually, the automotive industry is more probably the most severe, other than maybe drilling. I think oil drilling they may go up to even higher temperature. So Narendra says negative 40 to 160. That's we never go that. The highest temperature that I've seen is 90. So that's the highest that I've seen. Uh, we try to keep it to around 60. So yeah, we want to see what once it's in space, we can't fix it. It's gone. We can't do a service call, especially all the way to the planets. So once it's gone, it's gone. So we try to be as conservative as possible. I'm not sure if mass specs is going to go 200. They gave me a certain temperature. I don't want to say the temperature. I don't know if it's um, I'll keep the temperature to myself. Okay, I don't want to get anything. Yeah, because 200 C, that's a very. Oh, the test on, yeah, on mass specs, it went to vibration testing. Uh, so I think everything, it didn't fall apart. So now we're getting it back, and I think they're gonna hook it up and test it, see if it works. And I'm not sure what after that what happens, whether they do EMI, but eventually I'm pretty sure they'll do EMI testing. Southwest Research has its own testing facility there. As a matter of fact, Southwest is investing a lot of money. Uh, See, prior to this, we've always Southwest has only done instruments, and then once we do the instruments, we send it out to either JPL or Ball Aerospace. Those are the big companies that are actually building the spacecraft. So they get all the instruments and they put our instruments and everybody's instrument and assemble them and assemble the, the spacecraft. Well, Southwest now wants to get into that type of business. So they actually they're building a huge building, and we're going to be now in the business of building uh, the spacecraft itself, not just the instrument, but we're going to be assembling spacecrafts. So, but I'll probably be there at Southwest another 2 more years, and I probably won't be able to see that. I might stay there as a consultant. Yeah, the whole thing, or at least a big chunk, uh, is what they're thinking of doing. So, as a matter of fact, the building looks like the outside is already built, and I think they're retrofitting it. And it's supposed to be have a high bay with cranes and so forth. We do have a high bay in our old building. There, yeah. Oh, Pliskin, how do you know of Greg Miller? I'm interested. Do you work for Southwest Research? Greg Miller is the designer of Maspex. Pliskin, are you a Southwest Research employee, or are you from John Hopkins University? You work at Southwest? Okay, are you in the third floor or the second floor or the first floor? I'm in the third floor. Oh, you left Southwest Research. Ah, okay. Well, what floor did you work in? Did I ever, did, did we ever meet? Hey, Pliskin, did we ever meet? And what floor did you work? Okay, he's shy, I guess. Oh, you worked briefly with me. Well, what's your name then? Are you Ernesto? Oh, there was a guy, Ernesto. Is it you, Ernesto? You went to Austin, I thought. Now I remember you. It is Ernesto. Yes. Thumbs up. Oh, okay. He's in Emerson now. Oh, okay. Ernesto. Yeah. Okay. So I did work with you for a little bit. Cool. Well, hope you're doing fine. I'm pretty sure that if you ever want to come back to Southwest Research, I'm sure they'll take you back. Wow. Well, that's cool. Alrighty. Well, thank you guys for watching. Uh, I've had fun. I usually don't talk this much. I know that at work, I'm in my office and don't talk. I hardly, I'm always on the computer. Oh, that's another thing. When you have a computer job, you get fat. So be sure you don't get fat. Don't eat so much, or don't eat as much, out as much. Okay, Ernesto, take care. We'll see you guys. Okay, it was nice, enjoyable talking to you guys. Take care. Adrian, thank you. Power Path, thank you very much, sir. I will do the WCA. It's an interesting. I do remember someone wanted like over voltage, over current circuits, stuff like that. So those are good topics to talk about. Alrighty, guys. I'm gonna go ahead and see you later.